My name is Richard New. I run the research lab at Western Digital. And I'm going to tell you today about a couple of industry initiatives that we think are pretty fundamental and will change the way that people architect and build computers. And one of these is I'll call it open source hardware initiative, in particular RISC-V, which is a particular example of that. And then also a second one, which we'll talk about, which is sort of related to that, open interfaces. So the way that things connect into a CPU, and I'll talk about P4, but a use case that may not be exactly familiar to you, sort of a new use case for that. So hopefully you'll find this interesting. Let me skip this. Okay. This is actually an old version of the presentation, but that's okay. That's fine. So I'm going to give a brief introduction to our company. We're a data infrastructure company. We provide mostly storage solutions to our customers in the enterprise space and the retail space. So mostly these are either storage devices, SSDs, or hard disk drives, and of course storage systems, et cetera, or solutions for customers in retail. I'm going to talk about something that you may not be that familiar with. Hopefully some people are familiar with this, but I'm going to motivate this talk by talking about cache coherence, which is something I'll provide a brief introduction to this in case you're not familiar. So from a system perspective, if you look at, for example, this picture on the left here, which is a motherboard, a 4-socket motherboard, so it has 4 CPUs in it, and each one of those CPUs has DRAM attached to it. When you install an operating system on this system, from the operating system's perspective, it looks like one system, right? Even though there are 4 CPUs, whether you install your operating on a server with 1 CPU or 4 CPUs, it's one instance of the operating system. And the thing that enables that, by and large, is this cache coherency. What the cache coherency does, it does 2 things. First of all, it makes all of the DRAM in the system appear to be in one contiguous address space. And the other thing it does is it makes sure that all of the caches are consistent between the various cores. So for example, if you take a look at one of these CPUs, if you have a core on the CPU, that core can access DRAM on a different CPU, and it does that by sending these messages to the other CPU over this cache coherency interface. But you can see a problem in the picture on the right-hand side here. If you imagine that you have a bunch of cores and every core has its own local cache, if you have 2 cores that are accessing the same piece of DRAM, they may have both cached the same information in their respective caches. If one of the cores modifies the cache, the other cache is out of date or incoherent. So the cache coherency also makes sure that all of the caches for all of the cores are consistent or the same, right? Because if if they're inconsistent, then bad things happen. So that's kind of what cache coherency does. You could think of it as if you didn't have cache coherency, you could think of this as you could do all of this in software. You could write your software so that it makes sure that for any given core, it is not trying to access the same data as another core. You could think of it in the same way that you think of, if you guys are familiar with virtual memory. All modern CPUs provide virtual memory, which means that if you have 2 processes running on different cores, they appear to have their own independent address spaces. So when you're writing a program, you don't need to worry about where your program is going to be loaded in memory or what some other process may be doing. When you're writing a program, it appears to you like you have your own independent address space. So cache coherency is kind of like that. It makes it much, much simpler to write a program. If you don't have cache coherency, you can still do it, but it's very complicated. And I'll give you a specific example of how cache coherency works. So every core has its own cache. Every cache, you divide it up into cache lines, which are these 64-byte units. And then for every cache line, you keep track of the state of that cache line. So you keep track of whether you're the only guy who has a copy of that cache line or where somebody else has it loaded. You keep track of whether you have modified it, for example. If somebody else has modified it, then that cache line may be invalid. So you have to implement this algorithm. This is the cache coherence protocol that you implement across this bus. And you have the various cores and CPUs exchanging messages across that bus to make sure that every cache line has an appropriate state that's maintained according to this state diagram. And again, this is a thing that allows you to install a single instance of an operating system on a system that has multiple cores. So getting back to this thing of what would you do if you don't have cache coherency? Well, I'm not going to spend too much time on this, but you can write distributed software. If you have a system that, let's say you have you have a distributed system with a bunch of computers connected together over a network, and you wanted to write a program that runs across multiple nodes, you would write distributed software, which means that you would use something like message passing or RDMA to copy data back and forth between the nodes, and you would have to do that explicitly. And there are not too many people who write these distributed programs because they're difficult to write. And so you get back to this idea that you'd really like to have a system with cache coherency because it makes your job much easier as a programmer. So there are various ways, like various methods that you can deal with this from a software perspective if you don't have cache coherency. I'm not going to spend time on that. I'm going to instead move on to one of the other building blocks that we're looking at in order to build a kind of unique system that I'm going to describe. One of the issues with cache coherency is it's closely tied to the CPU architecture. You have an Intel architecture or an ARM architecture. Every one of those architectures has their own cache coherency system. They may or may not be available to you from an architectural perspective. So one of the initiatives, industry initiatives that I mentioned before is this idea of open source hardware. And Western Digital has played a significant role in this. There's an organization called RISC-V, which has defined a new instruction set architecture. So it's not an Intel instruction set architecture or ARM or any other MIPS or anything. It's a new instruction set architecture that is an open architecture, which means that anybody can go build a core or a processor using this new instruction set without paying any licensing fees or anything. So this is the RISC-V organization. It's a foundation that has roughly 150 members. There are not a whole lot of networking people there by and large, which is one of the reasons that we wanted to present this to the networking community. But the instruction set architecture essentially is the set of instructions, machine instructions, that a core can execute. So you think of it as the load, the store, all these, the add, the multiply, etc. All of these basic instructions that a CPU or a core can execute are defined by the instruction set architecture. This RISC-V is a new instruction set architecture that is open to everybody. And Western Digital has been, we were a founding member of this organization. You may not think I described us as fundamentally a storage company earlier, but because we ship a lot of hard disk drives and SSDs and storage systems, our devices have cores in them. In fact, we ship roughly 1 billion cores every year, so we have a strong interest in how this compute architecture works. Most of these cores are, of course, embedded cores, but we have, for instance, open-sourced the first production-grade open-source RISC-V core, which is kind of described here. It's available on GitHub, but it's basically an embedded core that you can go download for free and use to do what you want. And as I said, I think the networking community is not heavily involved in this open hardware initiative, but the networking community uses a lot of embedded cores. So this is an opportunity for to make that available to the networking community.
Is it a 64-bit core?
Most of these cores are embedded cores right now, but over time you will see 64-bit, superscalar, deep pipeline cores becoming available. So I mentioned this idea of cache coherency. One of the reasons I mentioned RISC-V is because we have cores that where, they're open architectures, we can get access to the cache coherency in a RISC-V architecture in a way that we cannot in some other instruction set architectures. So we are working with a partner, Sci-5, to basically create a system where the cache coherency now extends outside of the motherboard. So this is a picture here of basically a CPU This is a RISC-V CPU. There's a cache coherency protocol that is associated with RISC-V, which is called tile link. And what this CPU does something unique, which is it takes the tile link messages, the cache coherency protocol messages that are sent back and forth between the cores, and it will ship it out over the network. So essentially what it does is it takes a L1 Ethernet frame, and it stuffs the coherency messages into an L1 Ethernet frame and ships it out across an Ethernet interface. So that's where P4 comes in. So what we're doing is we're taking a network switch, a Tofino switch. We are basically, writing the P4 software that will allow us to essentially take these coherency messages and ship them back and forth where they need to go. And so we can create a system, we can create a larger system consisting of multiple nodes where that basically looks like it has one large memory domain. So I won't go into detail as to how this works, but it's pretty clear to you guys, I think, that if I take an L1 frame and I stuff it with some other type of packet or message, then I can use P4 to parse the message and figure out where to send it. So that's won't go into details, but that's the way it works. So this is what we're doing here. So we have on the right-hand side we have a bunch of these are pictures of CPUs, but imagine them as systems. And these systems are connected together through a switch, a Tofino switch. And each system will take the cache coherency messages that usually get passed around between the cores inside the CPU or between CPUs on a single motherboard. And we'll take these cache coherency messages and ship them out on an Ethernet interface in an L1 frame. That goes to this programmable P4 switch, which will route the cache coherency messages to other systems. And so what's really happening here is you imagine a bunch of servers that are connected together in this way, and instead of having two instances of a Linux server, you basically can install one instance of a Linux operating system across two different servers that are connected in this way. And the cache coherency will make it appear to the software as if all of the memory in both of these systems occupies a single address space. So from a OS perspective, it looks like it's one big machine. Now this clearly has a lot of, as you scale this up, this has a lot of implications in terms of failure domains, et cetera, which I'm not going to talk about today. But this is a way of, you can imagine this is a way of democratizing large memory systems. If you go out today and you buy, you can buy an 8-socket machine, it's very, very expensive. If you have a problem that requires a lot of memory, you want to do a large in-memory computation, you can buy a machine that will be very expensive that has lots of cores and lots of memory. This is a way of doing the same thing without having to spend that amount of money. And it's based on this open hardware implementation, which means you can essentially build without paying licensing fees. You can build your RISC-V system. You can hook it up through a Tofino switch, write your P4 code, which is also open source, and create this kind of a system. So this is obviously very preliminary, and in fact, this is just a recent result. This is extremely preliminary. This is a recent result where we have two machines that are hooked up. They're hooked up through a switch. You install a single operating system on them, and each one of these machines has 4 CPUs, but you install a single operating system, and it looks like the system has 8 CPUs. So this is just an example of an application. You want to have a question? Yeah.
One is the reason you use P4 is that.
So the reason you use the P4 is that the tiling protocol is proprietary, so it's not a standard Ethernet frame.
No, tile link is not proprietary. Tile link is actually open, but it's a coherency protocol, which means it bears no relation to any networking. It's a different kind of message that needs to be sent between these systems that's unrelating to any existing protocol. Okay. The reason we're using P4 and kind of stripping everything down to this L1 frame layer is that we need it to be fast, right? These are memory messages that are traveling back and forth between systems.
Yeah.
So ultimately, we need it to be very fast, which
That
is where
leads me to the second question. Can you give us some figures about what is fast and
Yeah, so we need this. We need
two
this
layers.
to be.
One is latency, the other one is jitter. So how sensitive are you to jitter?
I would say that we're not super sensitive to jitter. We're very sensitive to latency. Right now, this demonstration here is implemented on an FPGA, so it's very slow. This is an example of some of the timing. You can see it's already above 4 microseconds to send a message back and forth between two nodes. This is because this is on an FPGA that's running at 50 megahertz, right, which is not a realistic representation of what the system will eventually look like. But if memory, in order for it to function properly as memory, it needs to be submicron, certainly, right? Memory accesses will, depending on, people think that DRAM is 45 nanoseconds nominally, but if you put DRAM in a system and you take into account the fact that, you have to go to your page table to figure out what physical page you're addressing, et cetera. Memory accesses can take from 100 nanoseconds to 500 nanoseconds, depending on what you're doing. So we need the system to operate probably in the sub-microsecond regime in order to be useful, or close to the microsecond regime, which we believe is possible. So, but this is not what this is doing because it's on an FPGA. So that's really most of the presentation. What we're trying to do here with this particular project is to create an open memory fabric, which will allow us to build large systems which have very large amounts of memory in them, and essentially make the programming much easier and much more efficient than would be required if you had a full distributed system. This is one example of a project that we have on open interfaces, which is in turn, one example of this larger initiative across the industry of open source hardware. We have Western Digital, along with many partners, including Google and Alibaba, have started an industry consortium called CHIPS Alliance. CHIPS Alliance is an organization that will house open source implementations of various hardware projects. So the RISC-V Foundation is responsible for maintaining this open instruction set architecture, but the CHIPS Alliance will house specific implementations of cores and other projects that will be open sourced. So we wanted to, one of the goals of this talk here is not only to describe this particular project that we have relating to P4, but generally to make the networking community aware of the fact that there's this very large open source hardware initiative in the industry that could be applicable to networking infrastructure. So that's the end of my talk. Thank you very much.
So we do have some time for questions.
So it's hard for me to believe that you can go beyond one switch.
Go beyond what?
One switch.
It will be difficult to do that in sub-microsecond, probably. Yeah, if you want to do a couple of.
It's completely unpredictable, right? If you go,
yeah.
Even like the most lossless networks, if you think about it, the latency, the buffering, all this kind of stuff makes it very unpredictable. The tail latency is always going to kill a lot of application. I think this one is going to be very, very latency sensitive, right?
The jitter and latency doesn't matter so much. When you do memory accesses, there's a huge amount of jitter in a memory access anyway. If you just look at a normal system, again, DRAM itself, if you look at a DRAM die, it's 45 nanoseconds. But you have, for example, you have a page table. You have to traverse your page table in order to get to the page that you want to find. Some of the entries in the page table are cached in a TLB, right? A translation look-aside buffer. So very, very often when you're accessing memory, first of all, the CPU can prefetch stuff, And so it appears like the access is almost instantaneous in some cases. Sometimes the page table entry is cached in the TLB. Sometimes it's not, and you have to do a page table walk. So if you actually look at how systems operate and look at how long it takes to do a memory access, there's a huge range of times that it takes for a memory access. So memory jitter is the latency is an issue, right? The latency being like a microsecond or a few microseconds is an issue, but you have to compare it to the alternative, right? Your alternative is to design a system with multiple nodes where you're writing a distributed program, right?
Sure.
And there's no particular reason why a distributed program is going to be faster than doing load stores across the network.
Yeah, that's why a lot of people say that, okay, if I want to have a distributed system, I will just go for the flash and NVRAM. At most, I will not go for memory, or DRAM in this case. But I mean, if we can achieve that latency that you're talking about, it's amazing. But it's very hard.
Well, a few microseconds, let's say, is what you would need to achieve we believe, in order for the system to be useful, right? And again, you have to look at the alternative. If you can either, if you want to have a huge amount of memory on a system, and you can go buy a system that has a huge number of cores, or you can go to you can go write a distributed program to have a program that operates across multiple nodes.
And what was the reason that FPGA was not a good option for that switch? You used
it's just the first implementation. We're using a Tofino switch, so the switch itself is an ASIC, but the
FPGA.
Yeah, the individual nodes are implemented on FPGA right now, just because we have constructed this new architecture. It's not yet in an ASIC; it's in an FPGA.
No, 100%, I agree with that. I'm talking about the switch, the Tofino switch. Could the switching part become part of an FPGA? For better latency, for getting rid of the buffering, that kind of stuff. I'm just asking. Maybe.
No, I think a lot of the difficulty in doing this kind of stuff if you want to make a network or a memory fabric, there are many different kinds of memory fabrics that have been proposed in the industry, and different kinds of switches associated with them. The problem is that you can't beat Ethernet switches, right? Sure. Ethernet switches have by far the largest bandwidth, and it's difficult to find another switch like a PCIe switch or any other kind of switch that would have that same level of bandwidth. So for us, this P4 architecture allows us to use an Ethernet switch and essentially repurpose it. We cannot do this without P4, right? We have to reprogram the data plane. So this allows us to take a Tofino switch and repurpose it to a different end.
It was easier to do it.
Yeah.
As well.
In the original cache coherency protocols, when a CPU changes a piece of data in one of its cache and tells everyone else to invalidate it, I don't believe it expects an acknowledgement back, right, from the other CPUs that they invalidated. Would that be something you would need to build in this way over the network to ensure that actually incorrect pieces of data are gone?
Yeah, the cache coherency protocol that I showed is the simplest possible protocol that I don't think anybody really uses that protocol. There are different versions of the protocol. Some of them are directory protocols where you have some entity that is responsible for a particular location of memory and will keep track of who all has copies of that memory, right? So that would be a directory protocol where for a particular location of memory, you would, every time someone asks for that memory, you keep track of who has it. And then if someone else wants to modify it, you have to tell all those other guys who have it that someone else is either wants to modify it or has modified it. A non-directory protocol, if you don't keep track of who has access to that memory, you have to tell everybody, right? So it doesn't scale very well.
Right.
So there's many different protocols. Some of them with multiple hops. Some of them require that you would get a notification back, and so that's
okay.
Yeah, it's more detail than I can probably answer in this presentation. But.
Does this low-level messaging have the notion of drops or out-of-order messaging or anything like that?
The answer is the answer is no, not yet. Yeah, that's another huge issue that needs to be addressed. Yeah.
Did you try to use P4 to interconnect to various other system peripherals other than DRAM?
I'm sorry, I can't quite hear.
Okay. Did you try to use P4 to interconnect various other system peripherals, not just the CPU coherence, other than CPU coherence?
Yeah, if I go back to this picture, one of the reasons that we're interested in this as a storage company, and we have looked at, for example, providing non-volatile memories in the past, even NAND, which we are a vertically integrated company. We make we have NAND, and it's possible to make NAND pretty fast, right? So one of the reasons that we're interested in this is we sell storage and potentially memory, and we need to hook that up to processors, and we would like there to be sort of an open ecosystem of open interconnect ecosystem that would allow us to make products and sell them and connect to this architecture. So in this picture, you may have accelerators connected, you may have different types of memory. For some of these emerging memories, they're not as fast as DRAM. If you're hooking it up over a network fabric anyway, you may not care, right? It still may be useful, and so this would provide the opportunity to hook different things into this system that otherwise might not be possible.
Are you looking into any alternatives to Tofino, considering like the weirdness of Intel, CXL, versus like chips? Do you have alternatives?
So we started this project a while ago. I don't have any comment on Intel. I'd say the answer, we have not looked into other, if the networking industry develops in such a way that many switch vendors provide this kind of P4 programming language, that that would be interesting for us, and I think that's very similar to what we've heard in previous talks. So. One more question?
Can you repeat one more time why P4 is needed? Why can't I just do an ASIC there and solve the problem through an ASIC? Yeah.
Well, we would have to build our own ASIC. If we wanted to switch these kinds of packets, we would have to build a switch, right? And we would have to,
Is there a need for P4, or are you using P4 because it's just, you can use it? Like, can an ASIC solve the problem?
Pardon me?
Can an ASIC
if we were to build an ASIC from scratch, then we would, sure, we would not require P4. We could build a specific ASIC to act as a switch to switch these packets. But it's obviously an expensive proposition, and to do that, and we want to be able to leverage this whole industry that's spending a lot of money producing these switches with massive bandwidth, right? That's why we like the idea of doing this on an Ethernet L1 layer. So. Let's thank Richard. Thank you.